starting, the black body radiation expression that we obtained on Sunday was that the average energy is an integral from 0 to infinity of epsilon v pi squared c h bar to the third epsilon to the second beta epsilon minus 1 d epsilon. Something like this. Maybe there was beta epsilon upwards and there was 1 minus e to the minus beta epsilon. It's the same expression. So if we look on this, please notice that this is as saying, well, U is an average of the energy, and here we have the probability density function of this energy. So if we plot this probability density function of the energy, we obtain that it has some sort of a hump, and then it goes down. And so this is the spectrum of energies that we obtain from radiation of a body. So there is a cavity. Inside this cavity, electromagnetic waves are long-lived, so they don't dissipate. They are in equilibrium with the body. Okay, so with the walls of the whole realm. So here inside this we have radiation. This body have a specific temperature, which is uniform along the body, and by looking on the spectrum of the waves, right, we can understand what is the temperature of the body itself. Right? Specifically, if you see, there is a dependence of this is f of epsilon on the temperature T, which is exactly over here. So if we know the properties of the spectrum, or we can measure the spectrum, we immediately can determine what is the temperature. What is the temperature? Right? So it is temperature dependent shape. For example, all those infrared thermometers, how they determine the temperature from a distance. What they measure is not the temperature. They measure the radiation for specific wavelengths. Usually, they measure the ratio of three or two wavelengths. This is how they approximate this shape over here, and from this approximation, they can determine what is beta. Basically, what is the temperature? Okay. So the idea is not to measure temperature, but to measure the spectrum of the radiated waves, and from the spectrum of the radiated waves, using the theory of a black body radiation, to approximate what is the temperature. Now you can say, well, but our body are not black body, but and the radiation that coming from human body, from this board over here, it's different from a black body radiation because we are not in some sort of equilibrium. And this is right, but to a very good approximation it is. So if we include some other non-equilibrium effects, this will not change by much this shape over here. Okay? So the only thing that squeezed a little bit more, it can be this maximum can be shifted, but not by a huge amount. So this is actually a very good approximation for determining the spectrum of radiation from anybody. So this is how we also measure temperature from distance. For example, if you see publications of astrophysical journals, they can determine what is the temperature of the sun, what is the temperature of different stars, how exactly do they know this temperature? By approximating the emission from the star to a black body radiation, okay, an inclusion of small additional terms, we can measure the spectrum that arrives from a distant object, approximate the spectrum by this form over here, right? And by fitting it to whatever is obtained in experiment, we can find the different temperatures. Another nice thing that can be obtained is that actually this integral can be computed exactly. So if we take this integral, we have integration from 0 to infinity epsilon v divided by pi squared ch to the third, and here we're going to have epsilon to the third, 1 over e to the beta epsilon minus 1 d epsilon. Okay. Now we can take out all the things that we don't like, which is integral from 0 to infinity, the volume divided by pi squared ch h bar to the third, right? And inside we have epsilon to the third divided e beta epsilon minus 1 d epsilon. We can further say that, let's say that beta epsilon is x, epsilon equals x divided by beta, d epsilon equals 1 over beta dx. Okay. So we have, for our average energy, volume divided by pi squared ch bar to the third. The integration, the limit of the integration is still from 0 to infinity. So 0 to infinity. Here we have, instead of d epsilon, we have 1 over beta dx. Instead of epsilon, we have x divided by beta to the third power divided by e to the x minus 1. So in total, u is v pi squared ch bar to the third. And here we have 1 over beta to the fourth. So it's a Boltzmann over here to the fourth, t to the fourth, and an integral from 0 to infinity of x to the third divided by x minus 1 dx. Now, this is a number. It's independent of t, it's independent of the volume, of anything. It's just a number. And this is the Riemann zeta function of 4 multiplied by 3 factorial. And this is a Stefan-Boltzmann law. Stefan-Boltzmann law. Okay. That the average energy is proportional to the temperature to the fourth power. So we even don't need to measure the exact spectrum. We can measure the average energy that's emitted from a body, and then by using the Stefan-Boltzmann law, we can obtain this value t to the fourth. Now, usually we measure those properties of the black body radiation from different objects, as I mentioned, from by using thermometers or looking on stars and approximating the emission as if it was coming from a black body. And it works pretty well, although there are some small deviations and sometimes a little bit large, but it works pretty well. Now, there is one single observation for which this f of epsilon and epsilon, okay, is exact to any point. What I mean by exact to any point, so it's an experimental observation where there is almost no deviations between the the theoretical prediction of the black body and what we observe in experiments. Okay. This is a spectrum that is coming from cosmic background radiation. Now, what is a cosmic background radiation? So this is actually a nice experimental story. So there were two guys, Gonzalez and Oren, and they were astrophysicists, and they used radio telescope in order to measure different radiation spectrums, or that's in radio frequency, that's coming from the universe around us. And they had a noise in their signal. So they were pointing it's not a telescope, it's a radio telescope in different directions. And they always had some background noise that was interfering with the main signal that we are trying to locate. That was coming from specific stars or portions of the universe. They tried to get rid of this noise by any means possible. So they dismantled their telescope and they reconstructed it again. They saw that there were pigeons that were trying to build a nest on the telescope, and they got rid of the pigeons. So the pigeons came back, so they took them a while to get rid of the pigeons. Well, they tried to do anything, but no matter what they have done, they always had this background noise. Now, this background noise was exactly the same no matter where they pointed their telescope to, and no matter on the time of the year that they were trying to make their measurements. So basically, if this is the sun and this is the earth, so sometimes you're pointing in that direction, and sometimes you're pointing in that direction, and still you're getting the same signal. Eventually, the explanation, also by the help of some theorists, was that it's not a noise, but it's a phenomenon, a feature, right? So it's not a bug, it's a feature. So also it was for their experimental measurements. They came to the conclusion that what they are measuring is a cosmic background radiation. So according to the theory, astrophysical theory, there was a Big Bang. Afterwards there was a very fast expansion of everything, and the universe was extremely, extremely hot. So all the particles, there were no atoms, right? So the electrons and the neutrons, protons, or whatever you want to call it, were completely separate. Now, of course, there were other photons that survived, and they interacted with the free electrons and the free protons and the free neutrons. Mainly, they interacted with the electrons. Okay. Now, assume that you have many, many electrons and you have many, many photons. You should have some sort of equilibrium. Okay, so some photons are affected by the photon, and afterwards they emit another photon outside. So there should be some sort of an equilibrium between the matter and the photons that live or interact with this matter. Great, but the universe continues to expand. As it expands, it cools down. The moment it cools down, at some point in time, so approximately, according to the theory, for 380,000 years afterwards, the universe cooled down sufficiently such that there started interactions between the electrons and the protons, and they started to combine hydrogen atoms. Okay, now, the moment that the electron is combined with a proton, and you have an atom, hydrogen atom, it can no longer interact with those photons, with this radiation that it was interacting with previously. Why? Because in order to interact, now the electron had to obtain at least 13.8 electron volts in order to get over the gap that combines it to the nucleus. Right? So there has to be some minimal energy that the photon have in order to interact with the atom. But the radiation waves had no sufficient energy. So what happened is as if you had an equilibrium between electrons and photons, and what is called a recombination event occurred. So the electrons are now part or combined with nucleus. They are combining a hydrogen atom, and this wavelength or this radiation has nothing to interact with. Although there are atoms, but the atoms, like, you know, it's cutting through them like cheese. It has no absolutely no interactions because the energy of the photon is too low. So those photons are simply flying around in the universe, not interacting with anything, until they come up to this telescope of those two guys, and they start to understand it and see that, well, yeah, indeed, we have a spectrum that is not just some noise. It has a very definite spectrum that can be precisely described by this black body radiation. So this is the major proof of the Big Bang theory, right? So we have expansion of the universe and et cetera, but we can actually go and measure something that is predicted by the theory, and this prediction is that we should have a cosmic background radiation, and this cosmic background radiation, it's not just some radiation, it should have a very definitive spectrum of a black body, and this is exactly what we measure, right? So this is a proof, or one of the two major proofs for the Big Bang theory. Great. What I actually wanted to talk to you today are two things. One is generalization of the concept of entropy. And the other one is the Gibbs paradox. So I'm not sure that I will have time for both of those issues. So let's start with Gibbs paradox, because the next lecture maybe I won't need it. Okay, so let's start with Gibbs paradox, and if we'll have time, we also will talk a little bit about the generalization of the entropy. So what is the Gibbs paradox? It's not really a paradox, well, in some sense it is, but it's really a manifestation of quantum properties of the matter. So if we have a classical ideal gas, right? You have seen that we can build the partition function of this gas that we have for a single particle. So for a single particle, we have 1 over h to the third power. We have integrations over all the space, so dx, dy, and dz. Right? We can have from 0 to L, from 0 to L, and 0 to L. And we have integrations from minus infinity to infinity, minus infinity to infinity, minus infinity to infinity of e to the power minus beta dx squared divided by 2m plus dy squared divided by 2m plus bz squared divided by 2m dpx dp y and dp. So this is the partition function of a single particle that is sitting in a box. The dimension of the box is L by L by L. Now, actually, we have many particles inside the box. How many? N number of particles. But the assumptions of the ideal gas is that all the particles are not interacting with each other. So we forget about the interaction. They are classical. So the only thing that they have interaction with are the boxes, and the type of interaction that their volume, where they can live, is limited between 0 and L, and 0 and L, and 0 and L. Okay. They only have kinetic energy. Okay. And because they are not interacting, I can compute the Z, let's call it Z1, the partition function of a single particle, and afterwards, the total partition function is going to be Z1 to the power n. So Z is going to be Z1 to the power n because all the particles are identical. Okay. Now I can solve this integral, right? So what actually I do have to solve over here? I have to solve a bunch of Gaussian integrals, which is e to the power minus beta p squared divided by 2m px squared dpx. This is what? A square root of pi divided by 2 pi m divided by beta, right? The same goes for py, the same goes for pz, and integration over dx and dy and dz just gives me L. So in total, by using this formula, I obtain for Z1 L cross L cross L divided by h to the third power, and I have a square root of 2 pi m by beta from integration over px. I have a square root of 2 pi m divided by beta by integration over py, and I have a square root of 2 pi m divided by beta for integration over pz. Okay, let's take all of this into account, and we have Z1 is L to the third power, and I have here a square root of 2 pi m divided by h to the second power beta to the third power. So this is Z1. This is my partition function. And I know that the total partition function for n particles is Z is Z1 to the power of n. Okay, so what's the big paradox? Where this paradox is coming from? Why at all we have a paradox? Well, if we know Z, we can compute the free energy. Right? So what is the free energy? Is minus 1 over beta log of Z. This is the free energy for the canonical ensemble. Everything is nice. So let's see how it works. So it is minus 1 over beta log of whatever we have inside to the power n. So we can write here down n, and we have log of L to the third 2 pi m divided by h to the second beta to the third. Okay. It's not L, let's call it B. Great, or maybe not. We look on this, and then we ask ourselves, what's the problem with this expression? Is there a problem with this expression? So by looking on this expression, Gibbs basically said, aha, I have a paradox. Right. So what is wrong here? What do you think is wrong? Yes?
It's not extensive.
It's not extensive. Right. Free energy, energy, entropy, all of those guys, thermodynamic potentials, have to be extensive. Okay. Now, we can say, well, yeah, great, I have an n over here. That is why it's extensive. Well, this is true, but unluckily for us, we also have v. Okay. So the moment that we have v over here, all of this is not a linear function of the size of the system, right? Because of the presence of this v. So it's going like n log n. Okay. As n log n is not an extensive function. Okay. So what was the idea of Gibbs? How I'm going to solve this problem? Well, and this was Gibbs who built this idea of ensembles and canonical and microcanonical and grand canonical representations, right? Now, that either my theory is really, really wrong, or I have to do something. Now, how can I fix everything such that my free energy function is going to be extensive? Okay, so the thinking is, I'm not starting a new theory. I have already a theory. It should be okay. Something is wrong about this theory. Let's try and fix it. So how can I fix the behavior of this free energy in such a form that I should get an extensive behavior? Now this is quite easy, right? If you look on this function and you say, if only I had an n over here, okay? If only I had an n over here, everything should be great. Now, how I'm getting an n in this for this guy? Yeah.
There are 1 over n to the n.
Yeah. So if we put 1 over n factorial, okay, if we just put 1 over n factorial, let's see what happens. Because if I would have something of this form, okay, this is already an extensive function. Because this is extensive divided by extensive, so this is intensive, and I have only one extensive term over here, so the whole function becomes intensive. Okay. So the idea of Gibbs is somehow introduce an additional terms, and you already know the answer by maybe putting 1 over n factorial, such that we will cancel out this extensivity. Okay, so let's see how it works.
You use the stealing.
Yep. Because everything should work in large n behavior. So if we have this guy, so minus beta log of 1 over n factorial z to the n, which is minus beta log of z to the n minus beta or plus beta log of n factorial, which is minus beta. Here we have n log of v square root of 2 pi.
1 over beta.
1 over beta. Yeah, thank you. 1 over beta. 1 over beta. 1 over beta. 1 over beta. Thanks. So we have 1 over beta n log 2 pi m h to the second power beta to the third, and we have plus 1 over beta, and we're using scaling over here, which is n log n minus n. Now this works if n is large enough. Should be okay. So let's see. So we have n and n. So we write this down as 1 over beta n log of d a square root of 2 pi m divided by h to the second power beta to the third power minus log of n. And also we have minus 1 over beta n. Okay, let's combine those logarithms together. And we have minus 1 over beta n. And we have log of v divided by n, a square root of 2 pi m h to the second power beta to the third power minus 1. This is already an extensive function, right?
Plus 1.
This is already an extensive function. Okay. Why? We have a linear term over here. Here, the extensive v is divided by extensive n, so they cancel out the extensivity property, and everything looks great. Okay. So, by introducing this correction, saying I have 1 over n factorial, and I have to divide it by 1 over n factorial, works out pretty well. The only question that is still left is, why do I have to divide by n factorial? So the math is clear, right? The math is actually here is the starting point. Why I have to do this? In order to get an extensive function, okay? Now, but really why? Like, why do I have to introduce this 1 over n factorial in the z?
Because we are overcounting.
Because we are overcounting. How's that?
Since the particles are identical.
The particles are identical. So, okay. So this is the explanation that you're proposing is the following. If I have the particles, and the particles are identical, okay. So let's start from a specific configuration, and switch the position of the particles. Okay. And switch the position of the particles. What I will have to do is to divide all the total number of configurations by n factorial. So the idea is, where from I obtained this? This came from, I look on the different positions of one single particle, right? I looked on the different positions of one single particle. I computed z1, right? And I raise it to the power of n. So the procedure is, let's pick one particle, look on the combination of this particle. Let's pick another particle, look on the different combinations of this particle, and etc., etc., etc. Now, how many choices do I have? I mean, how many waves I can pick? The first, the second, the third, the fourth, etc., etc., etc. n factorial. Now, the claim is, all the particles are identical, so I have to divide, okay, I have to divide the total configurations, this, by the total number of different recombinations. So this is simply goes as 1 over n factorial. But the particles, I know which particle is which. So you're telling me that all the particles are exactly the same, and I don't care who I pick. But I can do this, the following discussion. I know that this is a red particle. And I know that this is a green particle. And this is blue particle. And this is purple particle. Oh, this is red. Black particle.
No, it's a superposition.
This is a black particle. Let's forget about the other. Okay. Now, what I have done, I followed all the different particles. So where the Z1 came from, I followed all the different positions. I followed all the different states of this red particle. And then I followed all the different states of the black particle. And I followed all the different states of the blue particle and the green particle. You're saying, it doesn't matter if you follow red or green or blue, they're all identical. But I can follow them. So when I switch different particles, okay, I know who is who. So you're saying, Stas, if they are all blue, so you don't care if you take this blue or that blue or this black, you don't really care who is who. But in classical mechanics, I know who is who. If I follow the system as a function of time, I will know that the red particle has went over here, okay, and the blue particle went over there. So it's a different state. You agree with me? So if a blue particle went over here and a blue particle went over there, I do not know who is who, and for me it's exactly the same state. This is why I have to divide by 1 over n factorial. But in classical mechanics, it's not true. So this is true in quantum mechanics. In quantum mechanics, I cannot follow particles. Even if they are identical, and I can measure this, I cannot say, well, I always follow this particle, and this is where it went. Okay. I have an uncertainty principle. I cannot follow particles. I can measure, and then I forget, and I measure again. And the particles can now travel wherever they like. I don't know where they went. In classical physics, theoretically it is. Okay? And all of this, of Gibbs, he had no idea about quantum mechanics. Theoretically, I look now on the system. I know this is green, this is red, this is black, this is blue. Okay? And I follow red, and red went over here, and I followed blue, and blue went over here. So this picture, okay, if I redraw it, is very different. So green stays over here, black stays over here, red goes downwards, and blue go upwards. You look on this, and you tell me, is this the same picture or not? It's different. So if it's different, I have to count it twice. I have to count this situation, this state, and I have to count that state. I shouldn't divide by n factorial. Okay. But I somehow do have to divide. If I don't divide, my free energy is not extensive, and I mess everything up. So what did it tell me? So this is the solution of the Gibbs paradox. If you divide everything by n factorial, you simply say to everybody, the particles are identical. But this is not exactly true, right? Because it works mathematically, right? It works mathematically, but if you think a little bit deeper, you say, but those are two different pictures. And if those are two different pictures, I should count this twice and not once. And what is the solution, actually? The solution is that this real, true representation of everything is quantum mechanical. And in quantum mechanics, we cannot follow all the particles. In quantum mechanics, if the particles are truly identical, they're truly identical, I don't know who is who. In classical physics, even if they are identical, I can follow different particles. But in quantum mechanics, I can't. And if the particles are truly identical, then, and only then, I can divide. I have to divide by the n factorial, because for quantum mechanics, there are no different colors. They're all exactly the same color of blue. And if they're all blue, this and that situation, picture, they're exactly identical. And I have to divide by n factorial. But if they're classical, something is wrong. And the solution is that everything is quantum. We can approximate something by regular classical mechanics, but quantum properties somehow burst out, okay? And we have to take them into account. So in some sense, the explanation of this 1 over n factorial is that, well, if they are truly identical, you cannot follow them. Now, but what happens for quantum mechanics? We see that in classical physics, we have to divide by n factorial. Because we don't know who is who, and this is the solution to divide. This works mathematically, right? But as I told you, if everything is quantum, then maybe in quantum mechanics we don't have to divide. So let's see. So we have classical picture, and we have two particles, particle number 1 and particle number 2. I can say they're completely identical particles, but in classical physics, I always can know who is 1 and who is 2. Why? Because I can follow them. In quantum mechanics, I can never follow particles precisely, and I can in classical physics. So if I have particle 1 and particle 2, and I plot here the different states that the particles can be. So this is state number 1, and this is state number 2. So I can have, in classical physics, that both particles number 1 and number 2 are sitting in state number 1, and no particles are sitting in state number 2. I can also have that both of the particles are sitting in state number 2, and nobody is sitting in state number 1. I can have the particle number 1 is sitting in state number 1, particle number 2 is sitting in state number 2, and I can have the particle number 2 is sitting in state number 1, and particle number 1 is sitting in state number 2. Okay. So these are the all possibilities. I have two states, I have two particles, either both of them are occupying the same state, like here and here, or they both occupying different states, like here and here. In total, how many different states I have in my system? Okay, so I have 1, 2, 3, 4. Okay, I have 4 different states classically. But if you're saying that they are identical and I cannot know who is who, well, I can, but I can't. Okay? I'm having this correction due to Gibbs, and I'm saying that this is the number of states. The number of states is 4 divided by 2 factorial, which is 2. I have only 2 different states, or this one or that one. This is the classical picture. Okay. What happens in quantum world? So in quantum world, I have either Fermi. Yes.
Why do you have only 2 and not 3? Why? I understand why 3 and 4 are the same because you can switch, but why 1, 2, and 3 are not?
What do you mean by this state? What do you mean? This state and this state?
Okay.
So so why don't I have 3? Symmetry?
But 1 is 2 is the identical states.
Not exactly. So this is 2 states, or I have 3. According to classical picture, I have to divide by n factorial. But I have to, so what does it mean that I have to?
I don't know.
Right? So I don't have 3 states. So this is a problem with the solution. Don't you think? Okay, so you've been convinced that you have to divide by the number of particles. We take a simple example where you have to divide by the number of particles, and you get a nonsense. What is this 2? Okay, but we are completely sure that you have to divide by n factorial. And you see that it brings you 2, and this is not 3, and then maybe there. I cannot explain it. Why I cannot explain it? Because the solution to Gibbs paradox that we use in classical physics is a mathematical fix, right? So you just have you have something which is not working properly. Say, oh, I'll push here the n factorial, and it works. It works mathematically, but it's not true. Okay. It's also not true because you have to go to the quantum world. In quantum world, you don't have to divide by anything. You just have to use proper statistics. So either Fermi or Bose. Alright, so you have all bosons or fermions. You don't have anything else. It's coming from what? Why do I have either Fermi or bosons? You know?
Exclusion principle.
So so odd solutions or even solutions, odd or even properties of the wave function. But yeah, right. So either Fermi or the boson, properties of the solutions of the Schrödinger equation. Let's see what happens in Fermi. In Fermi, I have 1 and 2, right? But in quantum physics, they are exactly identical. Now, what is the properties of fermions?
They cannot occupy.
They cannot be exactly the same state. So if I have state number 1 and I have state number 2, the only thing that I can observe is that particle number 1 is sitting in state number 1 and particle number 1 is sitting in state number 2. So the number of states equals to 1, not 2. Okay. What happens for Bose? Again, I have two particles, they are exactly identical. And I have state number 1, energetic state number 1, and energetic state number 2. Okay. So I can either plot particle at state number 1 and another particle in state number 2, or I can plot both of them to the left or both of them to the right. So this is the solution of 3, right? So the number of state is 3. So for real particles, for real quantum description, I can have either 1 state or 3 states. And in classical physics, somehow I'm getting 2.
The average.
Sorry?
It's the average.
It's the average. So what actually the Gibbs the solution to Gibbs paradox, this 1 over n factorial does, it somehow approximates, and it always is going to be like that, it somehow approximates, okay? It somehow approximates what? It somehow approximates the behavior of the Fermi and the Bose. Okay? Because 2 is, and you will get always something in between the solution of due to this division of n factorial. You get always in the classical picture something that is more than Fermi and somehow it's less than Bose. Always, right? Now, but it actually works. So you see, we can use classical statistics in order to describe physical matter, right? Where at least classical statistic works. Why is that? Okay, so why, at least where classical statistic works, usually for high enough temperatures. So temperature usually rules or ruins the quantum regime, right? So you usually observe some quantum stuff. You have to go either to photons or you have to go to low temperatures. Okay? Now, so for high enough temperatures where the classical picture works, somehow the fix, which is not true, should work. Okay? Now, why exactly it works for high enough temperatures? So, if we think about it, for high enough temperatures, the situation or the probability that two particles are sitting exactly at the same state is negligible. Okay? So for high temperatures, we don't have this state, and we don't have that state. We only have 1 and 2, and 2 to 1. So for high T, the number of states is 2 divided by 2 factorial, which is 1. Fermi statistics, it still stays the same. You have one particle in one state, the other particle in the other state, and you have number of states is 1. What happens for Bose? For Bose, the same ideology. You cannot have two particles exactly at the same state for high enough temperatures. So for T goes to infinity, the number of states is 1. Okay. So you see the Fermi and the Bose, they are converging exactly to the same result for high temperatures. Why? Because you don't have to count all the situations when all the particles are exactly at the same state. And miraculously, this 1 over n factorial that Gibbs inserted does exactly the same. It basically omits all the different situations when the particles are sitting or occupying the same state. And when you omit all those representations, you get exactly what you expect from Fermi and from Bose. Okay? So this is why it works. It shouldn't. and at least it won't for low temperatures when we need to use not the classical picture, but we need to use quantum representation, either Fermi or Bose. Okay. But for high temperatures, where you don't care about Fermi, Bose, and you don't care about quantum, this fix of 1 over n factorial, okay, it actually works. Why? Because it always approximates something that is in between Fermi and Bose. And when Fermi and Bose are identical, also our approximation is going to be identical to Fermi and Bose, which is one state. Okay, we are done for today. We are not going to generalize entropy today. We'll do it on Sunday. Thanks.